All right, so in the last class, we discussed about wireless networks, and we discussed some challenges of wireless. So namely, we had additional thermal noise, we had interference from other devices, and we have all the problems that come with the wireless propagation characteristics. So different parts of the different rays of the signal reflect from somewhere, diffract or refract from somewhere, and then they all get added up. Well, of course, because our class is just on network protocols and applications, the solutions to all of these problems that come with wireless are not our domain, but that is the domain of perhaps wireless communications or digital communications, where they deal with all these wireless propagation characteristics. But still, we learned about how to deal with, for instance, the interference, right? You already learned about TDMA and FDMA. Now you also learned about code division multiple access, or CDMA, where we assign different codes to each transmitter. What else did you learn? You also learned about the scheduling of Wi-Fi, where we deal with the hidden terminal problem. If two terminals cannot hear each other, but both of them cause interference to the same node, then it is very hard for them, because it is very hard for them to detect each other, they will be transmitting at the same time. But Wi-Fi and many other wireless protocols have certain kinds of reservation protocols where they perform RTS and CTS exchanges, ready to send, clear to send, and that can solve the propagation problem. That can solve the hidden terminal problem. Now today we are turning our attention to mobility. First, we are going to learn about challenges of mobility. Again, after some terminology, we are going to look at some mobility management principles, and particularly how it is being dealt with in IP networks, in the mobile IP section. And then we are going to very briefly have a look at the cellular networks to see how it's being handled in cellular networks. Okay, so let's turn our attention to mobility that these wireless networks enable. There is a spectrum of mobility. Some devices are not mobile at all, like the fridge at your home. It doesn't move every day. But even if you move some devices like your laptops, they may still be stationary from the perspective of the link layer. So if you keep attached to the wireless access point here, for instance, for 2 hours, even if you move from that seat to this seat, you're still not mobile from the perspective of the network. But somewhere towards the right-hand side of the spectrum, then we have devices that change their access over different access points. And on the right-hand side, perhaps we have a speeding car that is going from base station to base station, causing handovers among them. Again, let's go over some vocabulary, some terminology of what about certain terms in the mobility. So, first of all, we have our mobile device here. It can be a laptop, it can be a mobile phone, it can be any wireless connected device, it can be a machine device. It can be an IoT device attached to a moving factory part, or it can be an IoT device attached to a truck that's being tracked over different geographies. So this device has a home address assigned by its home network. So this home network can be the ISP, the first ISP it is connected to. You can think of this like the Synctel or StarHub or M1 type of ISP, Internet Service Provider. And it will be assigned with a permanent address by this ISP. So this permanent address will be the IP address that doesn't change even if it changes its point of attachment. And it can always be used to be able to reach this mobile. And this home agent is the router that performs the mobility functions on behalf of this mobile whose home network is here. This perhaps belongs to the ISP, Internet Service Provider. And after this home network establishes this permanent address, no matter where this device goes, this permanent address remains stable. Well, obviously, this router is connected to the wider internet. Can be a wide area network, can be internet. And there are other subnetworks over the internet as well. Now, let's say that our mobile has moved from the home network on the left to a foreign network on the right. So this is perhaps another ISP unrelated to the home network. And we call this the visited network. Maybe I should use blue color to make it easier to see. And, well, this visited network obviously has a different subnet mask. And once this device comes here, although its permanent address remains the same, it will be assigned a new temporary address by the visited network. So what we call this is the care of address, or COA. It will be assigned by the foreign network. And this foreign agent responsible for performing these mobility actions on behalf of this user when it is residing in this foreign network is called the foreign agent. So it is the agent that performs mobility functions on behalf of the mobile. Okay, so we just moved from left network to the right network. We got assigned a new temporary address, which we call care of address. And there is also this correspondent. Well, this can be any device, can be stationary, can be mobile, whatever. Correspondent is just the terminology I'm following. It's basically another device that wants to communicate with our mobile device. It can be your friend trying to communicate with you. Okay, let's go over a human analogy first. So let's say you had a friend from high school, Alice, and this Alice moved perhaps overseas, somewhere to the US, but you lost contact of her. You no longer has her mobile number. You don't know her address. So, and she doesn't use social media, let's say. So how can you contact her? What kind of protocol should you develop for you to contact her? Well, one way you can do this is to expect Alice to tell you where she moves every time she moves somewhere. But of course, she needs to tell not only you, but all her friends who might contact her in the future. Well, yeah, some friends do that. I sometimes receive WhatsApp messages, hey, this is my new number, please add. Maybe this is practical in the case of humans, but if we expect the internet to do this, it is huge overhead. I'll explain that later. And another, well, searching all phone books, of course, doesn't work because in the internet there is no such thing as phone book. You can perhaps expect her to let you know where she is, but again, this requires her to update all the friends around. Well, another option could be to call her parents, which in this case would probably be stationary. So she had parents, and they bought their house in Singapore, let's say, and they don't move around much. So if you know where they are, you can just contact them. Maybe they are still connected to landline, or they didn't change their mobile number, and learn Alice's new number, and then contact Alice. Or alternatively, you can just ask her parents to relay a certain message to Alice. And internet works in a similar way to handle mobility. Again, these options that we discussed, let the routing handle it, is like Alice telling you and all her friends where she is once she moves. And for a node to be visible to the network, it needs to be it should be addressable when it moves from one network to another network, right? So this is one way it can do this. But in the Internet's case, this requires updating a lot of routing tables. So let's perhaps go over this as an example. Okay. Yeah, never mind the rest of the slide. I'm using this portion. So Internet consists of autonomous systems, right? These are perhaps domains of different ISPs. Let's say this is autonomous system 1. This is connected to autonomous system 2. This is connected to autonomous system 3. And let's say Alice was here. And let's say this is autonomous system 4. And you were here. Let's say you are Bob. And all these autonomous systems have routing updates. They keep routing updates at their border gateway routers. So in 2's router updates, it will know that it can access Alice through autonomous system 1, so it will keep something like this. And 3 will keep this entry in its routing table. It can reach Alice through autonomous system 2, right? Because if anyone contacts 3, it needs to ask 2 where Alice is, which then routes that packet to autonomous system 1, where Alice actually resides. And for autonomous system 4, it will keep this entry. I can reach Alice through 3. And of course, 1 does not keep anything because it already has Alice in her network. But now let's say Alice moved from autonomous system 1 to autonomous system 4. Now, 4 needs to delete this entry and keep Alice here. And 3 needs to change this entry to Alice 4. And 2 needs to change to Alice 3. And 1 needs to change to Alice 2. Something along these lines. Well, if we do this for every moving mobile node, we need to update millions or maybe billions of routing table entries every day, every hour even. So in the Internet's case, this is not a practical approach. It is putting all the complexity at the core of the network, at the routers and switches of the network. This is not desirable. So if we let the routing handle it, for the 4 network to advertise all other networks that the mobile node is now connected to its network, it causes the exchange of routing information. And that routing information has to be propagated to all the autonomous systems. And this is not practical. It's not scalable to millions of mobile nodes that change its point of attachment every hour. Another option we have is, as in the case of contacting Alice's parents, we can let the AND systems handle it. So you see, again, the same principle of Internet, pushing complexity to the edge of the Internet, to the application layer protocols. And here we will discuss 2 routing approaches, indirect routing and direct routing. So indirect routing, the communication goes through the home agent. So it's like you contacting Alice and relaying messages to her through her parents. So everything goes from her parents to Alice. And in the direct routing, you just learn the location of Alice, and you contact her yourself instead of going through her parents. Okay, so we will be looking at these 2 in more detail soon. Any questions up to here? All right. Okay, so the first thing a mobile needs to do is to register with the new network. Now, in this example, our mobile was here. Our mobile was here, and then it moved here. And once it moves, it contacts the foreign agent in the new visited network. There is a certain protocol for that. And then this foreign agent knows that the mobile is here, away from its home network, and it learns about the home agent of this mobile, and then contacts this home agent. Hey, you know, your guy's here. Let me know if any packets arrive to her. I can forward them. And as the result of this, foreign agent knows that the mobile is here, and the home agent knows the location of the mobile. So this is just registration. So everyone gets updated about where this new mobile is. And then, let's say a correspondent arrives who wants to contact this mobile. To address this mobile, the correspondent obviously does not know the visited network of the mobile, where the mobile is. All it knows is the permanent IP address of the mobile, right? And because this permanent IP address belongs to the domain of this router, this home agent, any packets, any datagrams that is destined for this mobile will arrive, in fact, to the home agent. And because our home agent learned about the new address, the new care of address of our mobile, now it can relay, or in other words, tunnel these packets in step 2 to our mobile. In other words, it goes first to the foreign agent, which then forwards to the mobile. So this also shows you the two critical duties of the home agent. So the first one, it keeps track of the mobile's current location through foreign agents. And 2, it tunnels packets to the new agent, the foreign agent of the mobile. And after these packets arrive to the foreign agent, it will forward them. It will receive the packets and forward them to our mobile. Yeah. Okay, then one question to you is, let's say our mobile needs to reply to this message. A lot of protocols we saw, like HTTP's request and response sequence, it's two-way, right? Let's say our mobile needs to respond. Which route does it use, do you think? The options here are, well, it can send the packets directly like this, or it needs to go through the home agent. Which one do you think? Let's say this is route A, this is route B. Who thinks A? Who thinks B? Who thinks C? Anyone would like to explain who thinks A is the right answer? Why not B? Yeah. Well, okay. This correspondent, assuming it is not mobile, of course, its address is already known to our mobile device. Because in sending datagrams, it indicates its own address, right? And that address is known to our mobile. It doesn't need to tunnel the packets again through its home agent. It just directly addresses datagrams to that guy. So yeah, in number 4, the mobile replies directly to the correspondent. Well, of course, if the correspondent is mobile, then it's a different story. It still goes through 4, but it needs to contact the home agent of the correspondent, not the home agent of the mobile. So I think that's a tutorial question in tutorial 1. Okay. Okay, so this was indirect routing. But one problem here is that what happens if the user moves to another network, right? So it moved to a foreign network 1, but let's say it moves to the second foreign network. What happens then? Well, it's just the same protocol applies. The new foreign agent needs to register the new care of address with the home agent. And therefore, the home agent will learn about the new care of address. And any correspondent who wants to contact this mobile, again, will have to go through this home agent, which will tunnel the packets to the new foreign agent. Forget the old one, just the new foreign agent. So every time it moves, it needs to register the new care of address. As simple as that. Yeah. So with this kind of protocol, we can see that how mobility can be maintained. Even if our mobile moves from network to network, we can even maintain the TCP connections if these mobility protocols are handled effectively. So, just some comments about what we learned. So we learned about the permanent address, which is the constant IP address that doesn't change even if the point of attachment changes. So we can say that with this permanent address, the mobility is transparent to the correspondent. So the correspondent doesn't have to deal with keeping track of our mobile. And with the permanent address, anything it sends will be tunneled. It is therefore transparent from the perspective of the correspondent. And we also learned about that care of address, which is used by the home agent to learn about the new address of this mobile. In some cases, these foreign agent functions can be done by the mobile itself. Mobile can either ask the foreign agent to assign that mobile an IP address, a new care of address, or it can use some dynamic IP protocols like DHCP to get an IP address, to get a COA itself. But although this looks all very good, there is one potential inefficiency, not a problem, which we call the triangle routing problem. So as you see on this picture that we just discussed over, it looks like a triangle, right? And any packets sent from the correspondent have to go through the two vertices, two edges of the triangle. But the problem is, let's say this correspondent and mobile are very close. So this is the same area. Maybe both of you are here and you are texting each other, right? But one of you's, okay, let's think of this way. Let's say there is a foreign student here who came from the US, and the point of attachment for the mobile device of that user is some ISP in the US. But let's say that a student who came with exchange is texting to and from one of you's mobile devices. But when addressing that guy, all your packets will need to be routed from the home agent of this person, of this new student, and then come back here. So it has to go all the way to the US and then come back here. Well, this is obviously a little bit of an inefficiency, whereas you could, in fact, text him directly when you are very close. And to resolve this inefficiency, well, we have the direct routing protocol. So, most of it is similar, but the main difference is that now the mobile and the correspondent directly communicates. It doesn't have to be tunneled by the home agent. So let's see how it works. So the first thing that happens, again, well, obviously the care of address is all registered to the home network. That registration part is the same. But once the correspondent needs to communicate, it requests the foreign address of the mobile in item 1. So instead of directly sending packets, now it is requesting the new address. So it's like you requesting Alice's contact information from her parents rather than asking them to tunnel your or relay your messages. Well, the home agent of the home network will reply with the address, and then the correspondent will contact itself the foreign agent, because now it knows the COA, right? The COA was here. And then any packet that comes, any datagram that comes will be relayed through the foreign agent to the mobile. And again, on the way back, it goes directly from the mobile to the correspondent. So this overcomes the inefficiency of triangle routing, because we don't have to go all the way like this anymore. But this is, unlike the indirect routing, this is not transparent to the correspondent. The correspondent had to learn about the new address. It had to keep track of the location of the This is now 2d1 plus d2. All right, so this is done. So for B, we have non-persistent HTTP with the server configured for 5 parallel connections. Okay. So again, let's draw our new diagrams here. That is 4, 5. So in the first connection, this is our first, second, third, fourth, and fifth. First connection, let's say we start all from here. We open a TCP connection, and we receive a response. And then we send HTTP request and receive HTTP response to download the HTML. And in that HTML, we see, again, 5 objects. So we can now open 5 parallel TCP connections in every one of them to download every one of the remaining objects. This is the TCP, and this is the 5 objects. So this is object 1, object 2, object 3, object 4, and object 5. So in total, how many RTTs? That is 1, 2, 3, 4. So in B, we have 4 RTT zeros plus 2 D1. Nothing changes with regards to DNS, so I'm just using the same here. Any questions? Okay. So in C, now we have persistent HTTP with the server configured for 5 parallel connections again. So in persistent HTTP, we do not need to open a new TCP connection for every HTTP request, because we can use the old TCP connections that were opened before. So let's just erase all these. So here again, we still need to download the HTML object first. So we open a TCP connection. Well, when you open the TCP in the other ones doesn't really matter. Well, you can open them at first here, or you can open them later. So both are correct, I think. But so I'm opening TCP connections first in all of the connections here, because we might need to download something in the future, and we can maintain these TCP connections. And in the first one, I receive my HTML. And on the same connection then, I can also request the other objects. Let's say object 1, object 2 here, object 3 here, object 4 here, and object 5 here. I do not need to open another TCP connection. So how many RTTs in total? 1, 2, and 3. So that is 3 RTT zeros plus nothing changes with regards to DNS. Okay, any questions on these problems? I'll give you some more time to take notes. Okay, problem 3 then. So here we have the DNS, we have a DNS problem. So we have a local DNS server that caches all information coming from all the root, top-level domain, and authoritative DNS servers for 20 time units. For example, when a root server returns the name and address of a TLD server for .com, the cache remembers that this is the TLD server to use to resolve a .com name, and it keeps it in the cache for 20 time units. We also assume that the local cache is initially empty, and that iterative DNS queries are always used. So that is, our local DNS needs to go to each server in the hierarchy one by one and learn the address of the next one iteratively. And one time unit is needed for each server-to-server or host-to-server request response. And there is only one authoritative name server each for any .edu or .com domains. So we have the picture here, and the questions are here. Find the time units taken to resolve each of the following DNS queries made by the local host. So at time 0, the local host queries the name gaia.cs.umass.edu to be resolved to an IP address. So let's again draw our diagram here for DNS. So in solving these questions, you don't always have to draw these unless you're asked to, but I'm drawing them to make it easier to understand. So is that enough? So let's say this is our host. This is our local DNS. This is the root DNS. This is the TLD. This is the authoritative. And we don't need to draw the target host. Okay, so the first request is gaia.cs.umass.edu. And nothing is kept in the local host. So what happens is our host asks our local DNS server to resolve that. And nothing is kept in the cache yet. Our local needs to go to the root DNS server and obtain the IP address of the TLD server responsible for resolving .edu domains. So at this time, what happened is, I'm also going to keep track of what our local DNS caches. Let's say this is local DNS cache. At time 3, this is cached. That's edu IP address is cached. And after learning that edu, it goes to UMass it goes to the TLD server to learn about the UMass IP address, UMass authoritative server's IP address. So, or cs.umass, whatever the authoritative name server is for, it learns about the IP address of that. So at time 5, maybe let's say that is cs.umass authoritative server IP address. This was for TLD. And at time 5, this is being kept at the local DNS server. And now that it learned about the IP address of the authoritative name server, it can go to that authoritative name server and directly ask it about the IP address of the target, gaia.cs.umass.edu. It learns about that host's IP address now. And then, obviously, it needs to forward that response to the host. And our host, how many arrows are there? There are 8 arrows, each of them taking 1 time unit. So the answer then is 8. So it takes 8 time units to resolve that IP address. Any questions? Okay, so at time 1, then the local host requests that the name icon.org be resolved to an IP address. Let's erase this a little bit. Okay, so we don't need to go through the same drawings on the diagram because we can easily see that icon.org uses a TLD of .org, but UMass had a TLD of .edu, right? So these are different. They have different TLD servers. They have different authoritative name servers, and obviously they have different hosts. So the same process occurs this time for a different TLD server, different authoritative name server, but the time duration would still be 8 time units. But let's also take note of what happens, what kind of information is being cached in the DNS, in the local DNS. So because everything is just one step, 1 time unit away, I'm just going to increment these T numbers by 1. So at time 4, it will learn about .org TLD IP address. And at time 6, it will learn about ICANN's authoritative name server. And at time 8, it will learn about the exact host at icann.org, the IP address of the exact host that we are requesting. And it will then at time equals 9, it will forward that to us. But because the query started at T1 and ended at T equals 9, again, still the time to resolve that IP is 8 time minutes. Okay, so at time 5, we have cs.umd.edu to be resolved to an IP address. So we have here, again, an edu TLD server, but the authoritative name server would be different because this is a different organization with a different domain name. Instead of UMass, now we have UMD. Okay. So let's say time 5 is here. Actually, it would start somewhere maybe here, but I'm going to draw it below just to make it more easier to see. So at time 5, our host will send a query to the local DNS. And our local DNS server, because it already stored that edu TLD server's IP address, it doesn't need to query the root DNS server. Now it can directly go to that TLD server to query that new organization authoritative name server, that is UMD, right? So at time, what's that? This is 5, 6, 7, 8. At time 8, it learns about umd.edu's authoritative name server. And then from that authoritative name server, it obtains the exact host we are looking for, cs.umd.edu. That is at time 10, it learns about cs.umd.edu, the IP address of that host. And then at time 11, it informs, it forwards that response to the host. So it started at time unit 5, it ended at time unit 11, so the difference is 6. Okay, and in D, at time t equals 10, the local host again requests that the name gaia.cs.umass.edu to be resolved to an IP address. So all the servers in the hierarchy for resolving gaia.cs.umass.edu have already been queried at time t equals 0, right? We already have the IP address of gaia.cs.umass.edu stored at our local DNS server. So once that query happens, when was it? At time equals 10, right? Let's say at time equals 10, our local host queried the local DNS server. And because it is being cached in the local DNS server at time 12, our host will learn again about the IP address of gaia.cs.umass.edu. So that takes just 2 time units. And in item E, we have at t equals 30, the local host again requests that the name icon.org be resolved. Well, we already resolved icon.org, but that happened at time equals 1. But the local DNS caches only for 20 time units. So by the time we are at t equals 10, all these will be erased from the cache of our local DNS server, and again it will take 8 time units just as before. Right? Any questions? Okay, so I also uploaded the CA2 about socket programming. The deadline is, okay, I think that is 4 weeks from now on Wednesday. Please give it a read and let me know if you have any questions. So if you check the rules there, so you're free to ask questions, of course, about the assignment instructions, not about how to perform certain tasks in the assignment. But if you're someone who likes to do things in the last minute, in the last day, make sure you give it a through read first and understand all the tasks, because you cannot ask questions in the last 3 days. So you can ask as many as you want, but on the last 3 days, starting from Sunday night, you won't be able to ask questions until the submission day of Wednesday. Well, you can ask, but I won't be responding. So this is, just to be fair to those who already submitted, making sure that nothing changes after their submission is done. And also, I don't like responding to 10 emails on the last day of the submission. So that's one rule. So if you're someone who do things in the last minute, so make sure you understand it first. At least give it a read. Okay? If you have any questions, let me know. Otherwise, I'll see you on Friday. See you.